Okay, so we'll go through the practice problems from the first AP practice that we did. Let's see, this was from 420. So there were two problems on the assignment. The first one's a difference in population proportions. Right here, what I'm suggesting is that you kind of have a sample problem of everything ready. Your formula sheet's ready to go, and it'll help you be more efficient as you try to solve those two AP problems. So the process that we're taking you through right now is you're going to talk about, just pause it for a second. You're going to identify the process. You're going to write the conditions, show the mechanics, and interpret. Okay, so this is a confidence interval, I believe. Yeah. All right. So we're talking right now about the process, two sample, estimate for difference in population proportion, Z procedure. Okay, conditions. Unbiased data, independent simple random samples. Now that's because it's two samples. So they have to be independent and simple random samples. Okay, this one's pretty standard. Okay, the sampling distribution has to be close enough to the model that we're going to be using. In this case, it's normal to explain the sampling error. All that means is, as you take different samples, there's going to be variation between those sample statistics, just naturally because we're sampling. It's not a whole population. Okay, so this condition is met because we either expect or have observed more than 10 of each outcome. And that's just for proportions. For averages, it's very different. Okay. So we observe 52 and 111 for population A, 71 and 139 for population B, or sample B. Okay, now we're going to the formula sheet. Okay, so a confidence interval is statistic plus or minus the margin of error, which is the critical value times the standard error. Right now they're getting the statistics. There's the two proportions. Subtract those to get your statistic. Your standard error, okay, is going to be... let me explain why did I use this for our standard error. That's because when you're estimating a difference, there's an assumption that there is some kind of a difference. So you're not going to do that combined proportion. So you're not going to do that combined P where you'd add these. Okay, so that's a slight difference in standard error if we were doing a hypothesis test. All right, it's a confidence interval, so there's kind of an assumption that there is a difference or recognition that there could be a difference. So we keep them separate. Okay, so just carry that out. So get the standard error for this statistic. Now we get the statistic plus or minus the critical value, 1.645. That's the Z critical value for a 90% confidence interval estimate. All right, there's our interval. I like to put a diagram of that on the number line. Okay, so there's our number line diagram. It's a little bit favoring negative, but zero is still contained in there. Interpret the interval is huge. Please make sure that you do this well. So think of it as a repeated process. If we repeated this process for all possible samples of the same size, okay, 90% of those intervals constructed would contain the true difference in population proportions. What you're acknowledging is that you may or may not have, the true proportion captured, but the process is likely to do that. Okay. All right, so this second video that we attached here, we're answering this second part, which is kind of a hypothesis test in a way. But a 90% confidence interval acts like a two-sided hypothesis test at the 10% level. 90 and 10 is 100. That's kind of how it works. So what I'm doing right now is drawing a diagram with a hypothesis test and an interval kind of in the same diagram. Hypothesis test would have a curve. Interval would just be a number line. Statistics right there. So it's not exactly zero, but the interval certainly does. That's too narrow. Okay, too narrow. I should have had that out a little further. That left bound should have been out here a little bit. Sorry about that. That wasn't great. So the width of that interval up there was not quite wide enough, but oh well. All right, so this is going to be number 2. Okay, here's a number 2. Different problem. What we have is a 6-month exercise training program, 13 volunteers. Basically, what we did was we measured metabolic rates before and after. Okay, so same subject as a before metabolic rate and an after. Okay, so in this case, they didn't say a significance level. They didn't even say if it's one-sided. What I did was made an assumption that we want to see if the program increases metabolic rates or why bother, right? So I'm going to just decide that it's going to be one-sided. So I would expect after to be higher metabolic rate than the before the program. So I'm going to go after minus before and see if that comes out greater than or is greater than 0. All right, what I did was I let the calculator do all the work, or the spreadsheet do all the work. I got the differences. You'll have to do that by hand. Of course, this year we're doing this online, so maybe you can find a way. So just the differences, individual differences, I got the average of those. It's negative 3.44. And just the standard deviation of these averages is 6.4. I'm sorry, the standard deviation of the differences is 6.48. I did the graph only because, I didn't realize they mentioned that the differences were normally distributed. Usually we have to look at the graph if that wasn't mentioned to make sure there's no real skewness or outliers. Okay. So let's see, what am I doing now? Okay, stating what process I'm going to use. T procedure. Not a known standard deviation there. Sorry, I was a little quick. So now I'm writing the known alternative hypotheses. Okay. Real fast, you have to, if you're going to use symbols, you have to define them at some point. So the true population parameter, mu with subscript D, okay, is the true mean difference in metabolic rates after the 6-month program. For the 6-month program, I'll fix that. Okay. So now we go to what? Conditions, probably? Yeah, conditions next. Unbiased data. Unfortunately, it doesn't say that. It's 13 volunteers. Here's the issue that creates. I'll slow down a little bit. When you don't have a simple random sample, who knows? Maybe you've already taken people that are fit and put them through a program that's not as good as the one they're in. It could actually decrease their metabolic rates. Or, hey, if these folks are all people that never worked out before, well, of course, no matter what program you're going to put them in for 6 months, it's going to increase their metabolic rates. So we really do need a simple random sample of people if we're going to measure how this program is. It really wasn't met. So when this happens, we still run the process so you can answer the question and just put a disclaimer at the end, which acknowledges that the condition wasn't met. Okay, sampling distribution is close enough to the T. Again, explain sampling error. That's what the model's doing. It is met because the context says it is reasonable to assume the difference are normally distributed. Now, I go on to mention, because it's a small sample size, we would need that, or the sample itself should show no skewness or outliers. That's why I built the histogram earlier, in case that was something that I was going to need. Okay, now we'll go through the mechanics. I tried it once, forgot to delete that. Here it goes. All right, so now we're going to run through the mechanics for a T procedure. Hypothesis test, so standardized test statistic minus parameter. The parameter here is going to be 0. We assume there's no difference. And the standard error is the standard deviation over square root of n. And then there's your procedure. Okay, this is really critical that you demonstrate kind of where you're getting your p-value from. So if you put it on this t-curve, acknowledge there's 12 degrees of freedom. Remember, we lose 1 for matched pairs. If there's 13 subjects and we don't know the standard deviation, we're going to use the sample standard deviation. So we're going to estimate the standard deviation. We lose a degree of freedom there. So it's 12. Okay, the p-value, we're looking at bigger. We assume that if the program's any good, it's going to increase metabolic rates, and that's our approximate p-value. Always got to interpret the p-value. This is huge. Please make sure that you do a good job with this. Print it out, practice it. Okay, what we're saying is that this is the chance of observing a sample statistic as extreme or more extreme than the one we did, under the assumption that the null is true. Okay, in this case, 6-month program is no better. All right, did not increase or made no difference in metabolic rates. The decision here is that there is sufficient evidence at the 5% level to reject that assumption in favor of the alternative. So there is evidence the 6-month fitness program improved metabolic rates of the volunteers. Here's where the disclaimer comes in. Okay, we did not know if the volunteers were in fact a simple random sample, so this conclusion is not reliable, and a follow-up study should be conducted with all necessary assumptions met. There it is.